Hello guys, hi, welcome back. I'm pretty excited to do this problem with you. This problem is really something that I thought of while solving this year's ISI MStat problem. In the second problem, linear algebra, there was a question that find a matrix with certain eigenvalues or find a counterexample or something like that. So it's like a general version of this of that question is this that how to find a matrix with certain given eigenvalues. Let's say I give you a set of eigenvalues and tell you that find a matrix with its eigenvalues. So let's try to discover that step by step and let's uncover the secrets one by one. So now observe that these are the 4 steps we will look into, we'll discover. The first step is that now we already know that if we have a real matrix, we can find the eigenvalues, not only a real matrix, any matrix actually. How? By computing the determinant of a minus lambda I. It's pretty simple, right? Using the null space argument and this that all these arguments, you can find out that for which lambda, this is determinant is turning out to be 0. It's a polynomial, so you can find out the roots of that polynomial to find out lambda, the eigenvalues. Now, if I ask the converse problem, is exactly the problem that I started with. It's that given the eigenvalues of that matrix, can you find a real matrix with the eigenvalues? It's the opposite, a converse problem of that. So how can you find that? Let's try with a simple example. So let's let's say the eigenvalues of the matrix A are 1, 2, 2, and 3, including the multiplicity. So now this diagonal matrix actually works. We know that diagonal matrix actually works. The diagonal matrix is actually similar to the whole thing. Like similar in terms of the eigenvalues are similar. So the diagonal matrix has, if you put all the elements on the diagonals, you will have the eigenvalues to be 1, 2, 2, and 3. That's pretty normal, right? That's pretty simple. If you want to prove it, try to prove it yourself, okay? It's very easy. Like do 1 minus lambda I. So if you do 1 minus lambda I, like minus lambda minus lambda minus lambda minus lambda, like this minus lambda I, you will get this, and the multiplication will be this. The polynomial ka, the determinant ka. And hence from here you can see that the 4 roots are this, and it can at most have 4 eigenvalues of the 4 roots. So this is the idea that diagonal matrix actually works. Now, can we generalize it with real eigenvalues? Like let's say if the eigenvalues of a matrix are all real eigenvalues, and I have given the matrix, I have given the eigenvalues, can we find the real matrix? All the real eigenvalues of a matrix, like the matrix has only real eigenvalues. For example, a symmetric matrix has only real eigenvalues. So can you use that? Like, can you use the same algorithm to find a real matrix to find the matrix whose eigenvalues are all those real eigenvalues? So, yes, by just taking the diagonal matrix with the eigenvalues on the diagonal, just like I have shown it here. Right? It's pretty simple to solve for, real eigenvalues, matrix with only real eigenvalues. But the next natural question is that what about the complex eigenvalues? Given the eigenvalues with complex eigenvalues, given the eigenvalues of a matrix, which can be possibly complex, can you find a real matrix with those eigenvalues? That's a natural question. Next natural question. For example, the eigenvalues of A are I minus I1 and minus 1. Can you find that? This will not, of course, work. The same idea will not, of course, work. The diagonal idea, right? Why? Because it's not a real matrix. We want to get a real matrix. So how to get a real matrix? So what if we find out the eigenvalues of this portion I and what if we find out a matrix with eigenvalues I minus I and minus I, and separately 1 and minus 1? Can you find that? That's a very basic problem, right? Let's solve the 2 cross 2 first. I and minus I and 1 and minus 1. Yes, we can do that. For 1 and minus 1, we already know 1 and minus 1 is along the diagonal. For I and minus I, you can observe that this 0, 1, minus 1, 0 works. Why? Because if you do A minus lambda, you will get nothing but lambda square plus 1. A1 minus lambda, you will get nothing but lambda square plus 1 is equal to 0. जिसका solutions are in minus I. So this works. This is in fact a rotational matrix by 90 degree. Okay. But let's not go into the geometry of that. But the next natural question is that we have found out a matrix with eigenvalues I and minus I. We have found out a matrix with eigenvalues 1 and minus 1. Can we see that together to find our required matrix with eigenvalues I and minus I and 1 and minus 1? And yes, there is a beautiful way out there. And for that, we will go into this block diagonal matrix idea. So let's take this block diagonal matrix where, I mean, the idea is pretty simple that, you know, what if we can just block it like this, like 0, 1, minus 1, and 1, 0, 0, minus 1, and here all zeros are there. Like, that's the next natural way. It came to me naturally, and hence I proceeded like this. There can be other algorithms too. Here it's 0. So these eigenvalues are correspondingly that I minus I, and its eigenvalues are 1 minus 1. So it seems to be working. So now the mathematical check must be done, right? So that's why the block diagonal came up. So this was very natural to me, hence I tried to do in that manner. So if you consider this block diagonal matrix where these are square matrix, okay, placed along the diagonals, square matrix, just like I have shown. The size does not matter, okay. Like it can be 2 cross 2, 3 cross 3, whatever, but square matrices. So we can show actually that the determinant of this is product of the determinants, which seems natural, but it's like from the algebraic point of view, but not from a proof point of view. So it's a good proof that prove this, that the determinant trace is very easy to find out. It's easy, it can be easily seen because the sum of the diagonals is the same. The block diagonal, but the determinant is not same. You cannot do by eigenvalue because I will be using this result to find the eigenvalues. So do it by some other way, or maybe some other proof, or maybe you can prove the eigenvalues by different some method. I will be doing that after this. So my suggestion is you can do it by induction. Why? What if you just start with these two matrices? Because a block diagonal attached with another block diagonal is another block diagonal matrix together. So if you attach it A3 here, it will become another block diagonal, right? So my question is that what if you just find out for this two matrix? Two matrix can you just find out? Two block diagonal matrix. Try to find out that. Try to observe that this determinant is equal to determinant of A1 and determinant of times A2. There's a general blocked partition matrix of determinant. You can also use that. But here you can use it other different methods because you have the zeros here. You can imagine and you can find out the vectors. So try it out. It's not very hard. It's not really very hard. So we have got that the determinant, we have assumed this one here, assume the determinant of A is product of the determinants of the block, the block matrices along the diagonals. So let's move to the next part. What about the eigenvalues? So if you do A minus lambda I, observe that it becomes A minus lambda I correspondingly here with the corresponding dimensions of A1, okay, of that I. Okay, if you imagine this, that A, B, C, D, and P, Q, R, S, and all 0, 0 here. If you do A minus lambda I, it will become minus lambda minus lambda minus lambda minus lambda. So it's actually this minus lambda I, and this is actually this PQRS minus lambda I. So this comes up very naturally. You can think about that, how it comes up. So the product of this, determinant of this is nothing but the product of the determinants of this by the previous result in the previous page. So we get therefore that A minus lambda I has exactly the same eigenvalues as A1, A2, and AN. That means eigenvalues and eigenvectors of A are simply those AKs of those AKs combined. And that's pretty a strong result, right? It's a beautiful result actually. Now if the problem is almost solved, that therefore this intuition was correct. We can actually make that block diagonal to form the eigenvalues with the matrix with the given eigenvalues. So let's check out the matrix here. So the eigenvalues will be of the matrix with eigenvalues I minus I and 1 minus 1 will be the following. We just put the block diagonals as this corresponding matrices, break it up into pieces of complex and real number pairs and put it into the block diagonal matrices by finding the matrices. Great. So let's see what's the algorithm once. Pair up all the eigenvalues in complex pairs. Find the AKs with the corresponding paired eigenvalues. Find the real matrix with all the real eigenvalues. Put it along the diagonal, and take all the matrices together and make it into a block diagonal matrix. Right? Pretty simple, right? So let's watch an example. Let's solve an example. Let's watch me solve an example. So, but before that, the next natural question comes that for I and minus I, it was pretty easy. But what do I want to have a matrix P, Q, R, S, or A, B, C, D, whose complex eigenvalues are Z1 and Z1 star, because they must occur in pairs, because it's a real matrix. Z1 and Z1 star. That's the fundamental question. Otherwise, we cannot pair up and find that matrices, right? Like we did for I and minus I. For I and minus I, we did what? But this was an introspection, right? We didn't show a general algorithm. So what if what is the way to find the general case in the matrix for the general case Z1 and Z1 star? Let's find that. So I will show you the algorithm. So observe that we know that the trace of this matrix is Z1 and Z1 star, which is a real number P. It should be known because Z1 and Z1 star are known. And determinant of A is nothing but product of these two eigenvalues, Z1 times Z1 star, which is also a real number because, and it's known because we know Z1 and Z1 star because it's a real matrix. So therefore, we know that we need to find A, B, C, D, right? We know that trace is equal to A plus D and determinant is AD minus BC. So can we solve this equation somehow? Yes, we can. So we know P and Q. So the problem boils down to solving A, B, C, D in terms of P and Q. And observe that if there are 4 variables and 2 equations, so we can actually reduce down certain things. Like we'll see that how we can. So observe that if you do P square minus 4Q, the first part is when you have given A plus D, you should be trying to find A minus D. This is nothing but A minus D whole square. P square minus 4Q, nothing but A minus D whole square. A square plus D square minus 4AD plus 4BC. Right? So if BC is negative or positive, it depends, right? So therefore, P square minus 4Q, this is known, and just remember this, minus 4BC is equal to A minus D whole square, right? And we know A, and therefore we'll understand this very carefully that since this has complex matrices, complex eigenvalues, this may not be positive always. This can be negative. So we can adjust this to make it positive. So what we do instead, we make it to 0 so that A is equal to D. We can make it to 0. So we get BC is equal to what? P square by 4 minus Q. So we get A is equal to D because these are real numbers. And therefore we get A is equal to D is equal to, and the sum is P, so it will be P by 2. So we get A is equal to D is equal to P by 2. And BC is equal to P square by 4 minus Q. So we put B is equal to 1, and therefore C must be P square by 4 minus Q. So therefore the matrix, if you know the trace and determinant to be P and Q, the matrix P by 2, 1, and here P square by 4 minus Q is a matrix with eigenvalues Z1 and Z1 star, where the trace and determinant are defined like this. Pretty interesting and straightforward, right? So let's try to apply the entire algorithm in a single problem, finally. So we have found out how to find a 2 cross 2 determinant matrix. So we have to find the eigenvalues with complex eigenvalues. We have to find a matrix with complex eigenvalues 3 plus I and 3 minus I, 2 minus 3, 8 plus 2I and 8 minus 2I. So therefore, first is pair of the eigenvalues, complex eigenvalues, 3 plus I, 3 minus I, We have 8 plus 2i, 8 minus 2i. And we have here 2n minus 3. It can be minus 5 added also, does not matter. So therefore, let's try to find this one. So trace is P is equal to 6, right? And P and Q, the determinant is equal to product of this, we get 10. Here P is equal to 16 and Q is equal to determinant is equal to 64 plus 4, 68. Pretty good. So the matrix was what? P by 2, so 3 and 3. And P square by 4 minus Q, right? P square by 4 minus Q. So 1 here. And P square by 4 minus Q. P square by 4 is 9 minus Q is minus 1. 36 by 4, 9 minus 10 is minus 1. And here P is equal to 16, so it's P by 2, 8. Here it's 1. So P square minus by 4, 16 square by 4 is 64, minus 68, it's minus 4. So therefore, this matrix has eigenvalues 8 plus 2i and 8 minus 2i. This matrix has eigenvalue 8, 3 plus I and 3 minus I. And this matrix is eigenvalues this. So what we do? We just make it into a block diagonal like this. This matrix, 3 matrices are there. Three I minus I 3, 8, 1 minus 4, 8, and 2, 0, 0 minus 3, and all 0 otherwise. That's pretty easy, right? That's pretty interesting also. So I found a general algorithm to find out a matrix with a certain eigenvalues, even it's complex, real, whatever it is. This algorithm also follows for real because it's just extension of the real idea. So I hope you enjoyed this as much as I did. And yep, so if you enjoyed this problem, do share among your friends, like, subscribe, and whatever you love to do. Comment your different ideas, whatever in different way you solved it. And if you're interested in some courses we are offering, you can check our links below. And all the best. Stay tuned, stay blessed, and keep supporting us. Thank you guys. Bye bye. I will see you in the next video.